Hi, welcome back. So today we will study the power spectral density of BPSK signal. So before that, we will first try to you know model BPSK signal at baseband. In terms of some random signal, random process. So we will mimic BPSK as a random binary wave. I will explain what it means. A random binary wave. So what does random binary wave mean? BPSK symbols are a series of, suppose you have ones and zeros, and you convert them using non-return to zeros signal. So as an example, suppose you have 1 0 1 1. Let this be the output of pulse code modulation. And after you, how do you convert into BPSK signal at baseband in BPSK symbols? So you will you will map to some positive level plus a, suppose, and 0 you map to minus a level. So this is called NRZ, no return to 0. So this signal in baseband you can call as BPSK, and then you basically modulate it using cos of omega ct, and you get the BPSK signal in the passband. Now let's work right now at the baseband. So now if you see the source of a binary source, if you see, you can just look at it as zeros and ones are coming randomly from the source. Okay, so now if I denote by x of t, so let x of t denote this random binary wave. Okay, now let me plot one of the realization of this wave. Suppose I will plot, sorry, small x of t. One of the possible realizations is like this. So what it will be in terms of binary? So this is 0 0 1, then again 0, then 1 1 0 1 1. This is again 1. Okay, and the time interval for symbol period is capital T. Okay, now this is your origin. See, this is your origin. Okay, what can happen is, to model it properly, first of all, where 0 is mapped by minus a, this is minus a, and 1 is mapped by a, okay, plus a, and we can see that in general the pulses are not synchronized, in the sense the starting time of the first pulse, it can start, suppose here, if you see from away from the 0 point, let's take this as some td. Okay, so as another example, ideally you want the pulse should start at time t is equal to 0. Okay, but it can start like this also, right? So, or it can start like this also. So it's not usually synchronized in this sense, right? So around this time t is equal to 0, this pulse can start anywhere, and I denote that time by this td. Okay, and since we treat it as a random process, because we don't know beforehand what pulse will be coming, whether it is plus 1 or minus, whether it is 1 or 0, and at what time it will start, we don't know it. So we can model this starting time. Okay, so this td is starting time, and it lies between, right, it can be 0 to capital T. Now we can think of this td coming out of a random variable capital Td. So this is a random variable which is uniformly distributed. Uniformly distributed, over the time interval 0 to t. I will explain what it means. So when you say uniform distribution, so if you plot the probability density function of this, this time, which is a starting time td, so let this be td, and let this be ftd of td. This is the probability density function of the starting time. It is uniformly distributed between 0 and t. If you recall the definition, if you have a uniformly distributed random variable, that is, its probability density function remains constant in this range. Okay, and in fact the height will be 1 by t, so that the total area is 1. So you can write this PDF as f td of td is 1 over capital T 0 otherwise. See, I repeat what I have done. Let me go back here. If you look at this x of t, this is the time t is equal to 0, and since we are treating it as a random process, so signal can be either plus a or minus a, and it can start, it's not necessary that the pulse will start rising at t is equal to 0, right? The starting time can be delayed, there can be delay in the synchronization, so I denote that by td. Now even that is a random, so how we assume that since it can take any value between 0 to capital T, right, because capital T is the duration of the bit, duration of this pulse, so this starting time we treat as uniform random variable, a random variable taking uniformly values between 0 to t, that is, its probability density function is constant for time 0 to capital T. So hence we can write its PDF like ftd of td is 1 by t. And in between any time, okay, suppose you are at any point of time, the pulse is 1 or 0, that comes up with, there are equal chances that it can be 1 or 0. Okay, equally likely. Now what is our goal? See, our goal is to find power spectral density. Okay, I recall that,
so this is the projector on,
sorry, so I recall that the definition of power spectral density, the classical definition, is the Fourier transform of autocorrelation function. So now here we are treating the binary wave as x of t, right? We will first need to find its autocorrelation function. Once we find its autocorrelation function, then we take its Fourier transform and we will get the power spectral density. That is our goal. Okay, so you know that how to compute autocorrelation function. Suppose I have two time intervals, let it be suppose tk and ti. How do I compute autocorrelation function? I will compute the expected value of right, and if this expected value depends only on the difference between tk ti, then we know that process is in some sense stationary, and then we can find it. Now these are two different time intervals, tk and ti, two different points. Now let me go back to this figure, right? Suppose tk is this and ti is here, right? This is the one case. So in that case, tk and ti lie in the two different pulses, right? And hence when tk ti lie in two different pulses, they are independent of each other. Because this is a random pulse coming up, so every time the value you get at one time is independent of the value you get other time. So if we take as case 1 that this tk minus ti, difference between the two is greater than t. See, t is the pulse duration, right? Suppose any pulse cannot exceed the time t. So tk minus ti being greater than this means, suppose if this is tk, then ti cannot be here in this range. It has to be here or here or here. So if tk minus ti is greater than t, then it means that that x of tk and x of ti occur in different pulse intervals. Okay, and hence are independent, Now if it is independence, then you know that expected value of x of tk, x of ti is expected value of x of tk Now what is the expected value of this signal? I will not go into detail, but if you look at that, it is random plus a minus a plus a minus a. On an average, the value will be 0. So the average value of the signal is 0. So hence this expected value is 0 times 0 and 0. Okay, so case 1 is solved. Now we can have case 2, that this tk minus ti is less than t, right? So the case is like this. So this is a capital T. Suppose you pick up tk here, then ti must be somewhere within this pulse. So now when this is the case, then the x of tk, x of ti, they will be correlated with each other. It will not be independent. Okay, and further, if you look at this delay part, suppose if signal is like this, so this is the td, right? Now this TD also has to satisfy this condition. Why it has to satisfy this condition? That for x of tk and x of ti to occur in same pulse. Okay, let me take an example here. Suppose this is here TD, right? Now you can have TK here and TI here, right? And difference can be less than T, but they occur in different pulses. Now for these two to occur in the same pulse, these two time intervals to be in the same pulse, right? So you need that this TD should be less than this capital T, right, minus the difference between the two. Now if you look at here, if TD and TK will lie in different pulses, this condition will not be satisfied. But if the scenario is like this, so this is the T and here is TD, so TK, here is TI and is the TD. So in this case you clearly see that this is the T, capital T, and this is TK minus TI, okay, and this TD is clearly less than T minus TK minus TI. Okay, so in any other case you will see that this condition will not be satisfied. In any other case, the if TK and TD if they TK and TI, if they are in different pulses, then DD will not be less than the difference between T and TK minus TI. This point may be difficult to ponder upon initially, so but if you think it properly you will get it, but initially it will be a little bit hard. So we have to go through the proof again and again. Now under this condition, the expected value of x of tk, x of ti, but this expected value we are computing for a particular td, right? So I will write here, given td takes some value td, okay, for a fixed this delay time, or for a fixed synchronization time, okay. So then this expected value is, what is its value? See, tk and ti, they can lie in the same pulse, then the amplitude of the pulse will be a, right, or it can be minus a. So x of tk can be a, x of ti will be a, or x of tk is minus a, x of ti is minus a. In both the cases the product will be a square, right? And for them to be in the same pulse, you know the condition that this TD is less than T minus mod of Tk minus Ti. Okay, and if TD is not having this value, right, then they are independent of each other, and hence its value is 0. Right? If T if Tk and Ti, like they are in the different pulses, then you know x of Tk, x of Ti will be independent. So hence its value will be 0. Okay. Now this expectation is for any particular fixed TD. Now if you want average over all the TDs, suppose I want expected value of, see, here is something which will be new for you. Okay, don't worry about the symbol. See, this expected value here is with respect to the random variables x of Tk, x of Ti, this one. Okay, this expected value is with respect to this TD. Okay, because we were fixing here TD, now we are taking this also as a random variable. Now what it will be equal to? See, it will be equal to integral of whatever value x of Tk, x of Ti is having, times the probability density function, right, of the time TD. Now we know that expected value of x of Tk, x of Ti, right, that is equal to a square whenever TD is between 0 to T minus Tk minus Ti. Okay, and the probability density function is 1 by T, right, dt. Okay, so this we can write as a square by T times 1 minus so or if we write it directly, so T, sorry, let me erase it, a square by T, so T minus mod of Tk minus Ti, right, and this we can write as a square times 1 minus and we know the condition that Tk minus Ti should be less than T. This is well known. Now if you see that this exactly is RxX autocorrelation, and if you define Tk minus Ti as tau, then we can write the autocorrelation function as a square 1 minus tau by T whenever tau is less than or equal to T, 0 whenever tau is greater than or equal to T. Sorry. Okay, now in this short lecture we will just stop here, and then in what we have to do, we have to find its Fourier transform. But I request you again go through the lecture, try to ponder on some points. Okay, because some of the things are a little bit you need some geometrical visualization. So we got the autocorrelation function for a random binary wave which mimics BPSK signal. In next lecture we will then derive its power spectral density.